Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we're going to rebuild our whole neighborhood from nothing. Not from planets, not from stars, but from the dark, cold clouds that float between the stars of our Milky Way. We're going to watch that cloud collapse, flatten, light up a brand new sun, and then slowly sort itself into rocky planets, giant planets, belts of leftovers, and distant icy wanderers. This is the history of our solar system, told from the beginning, the real beginning, 4.6 billion years ago. Get comfortable, let your thoughts drift out past the moon, and imagine the sky before there was a sky. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world. And thank you so much for being here. Before there was a sun or an earth or even the idea of planets, there was just a part of the galaxy that was a little thicker than its surroundings. The Milky Way is full of these things, giant molecular clouds made mostly of hydrogen gas, with a pinch of helium and tiny grains of dust. They are cold, only a few tens of degrees above absolute zero, and because they're cold, the atoms and molecules inside them move slowly, so gravity has a better chance of holding them together. For a long time, a cloud like this can just float, drifting around the galaxy, lit faintly by distant starlight. But these clouds are not perfectly calm. A nearby supernova shockwave can pass through. Two parts of the cloud can bump. The cloud can cool enough that its own weight finally matters. When that happens, a section of the cloud starts to contract. Gravity pulls inward from every direction. As that contraction begins, the slight spin that was always there becomes more important, because when you make something smaller that is rotating, it has to rotate faster to conserve its angular momentum, like a spinning skater pulling in their arms. That's the same physics here, so the collapsing region doesn't fall straight into a point. It flattens into a kind of cosmic pancake, a rotating, thick, dusty disk with a growing, brighter knot in the middle. That knot will become our sun. The disk will become everything else. Inside this disk, the conditions are suddenly very different from the original cloud. Near the center, it's warmer because energy is being released by the infalling gas. Farther out, it's still cold. In the warm region, ices can't survive. In the cold region, they can. That simple temperature map, hot inside, cold outside, is going to decide hundreds of millions of years later which worlds get to be rocky and which get to be giant and icy. But right now, in this first stage, nothing looks like a planet yet. It's just dust grains bumping, sticking together thanks to electrostatic forces, making slightly bigger grains, in a disk that is turning and feeding material into the center. The whole thing is quiet, slow, and extremely patient. If you could watch it in fast forward, you'd see a swirl grow tighter and brighter, like water spinning into a drain, except in this case, the drain is a forming star and the leftover water becomes a family of worlds. As the central lump, the protostar, kept swallowing gas and dust from the disk, it got heavier, and heavy things under gravity get compressed. Compression heats material. Deep in that forming star, hydrogen atoms were being pushed closer and closer together. At first, the young object just glowed because it was hot from falling material. But at some point, the pressure and temperature in the core got high enough for hydrogen fusion to start. That's the key transition. When hydrogen nuclei start fusing into helium, huge amounts of energy are released. That energy pushes outward. Now, instead of collapsing unchecked, the star reaches a balance. Gravity pulling in, fusion pushing out. Our sun was born. That newborn sun was not as calm as the one we see today. Young stars tend to spin faster, flare more, and blow stronger stellar winds. That wind, a stream of charged particles, began to sweep through the disk. Close to the Sun, the wind and the rising radiation stripped away lots of the leftover hydrogen and helium gas. Material that hadn't yet been incorporated into growing planets was simply blown out of the inner zone. That matters because it meant the small rocky things growing in the inner disk suddenly didn't have access to the big puffy blanket of gas anymore. They had to make do with rock, metal, and whatever volatiles they'd already trapped. Farther out, though, beyond a certain distance, it stayed cold, and the Sun's cleansing wasn't as complete, so ices could survive and gas could still be gathered. This line between too warm for ices and cold enough for ices is often called the snow line or frost line, and it's one of the most important invisible borders in our planetary system. Inside of it we got Mercury, Venus, Earth, and Mars. Small, dense, rocky. Outside of it we got Jupiter, Saturn, Uranus, and Neptune. Worlds that started with a solid or icy core and then became huge by pulling in the surrounding gas before it was gone. So the moment the Sun turned on, the disk stopped being just a soup of building material and became a place with rules. Hot in, cold out, rocks in, gas and ices out. The Sun also took most of the mass, more than 99%, leaving only a thin fraction in the disk to build everything else. That's the part we live in, the leftovers from star making. Once the Sun was shining and the disk had its temperature zones, the inner part, the region that would one day hold the terrestrial planets, became a busy, dangerous construction site. At first, everything was tiny. Dust grains stuck to other dust grains. Static electricity helped the very smallest particles cling. As clumps reached centimeter and meter sizes, collisions became more violent, but some of them still stuck, especially if they hit slowly or had icy or dusty coatings to absorb the impact. The key change came when some of these clumps reached a few kilometers across. At that size, their own gravity started to matter. A 10-kilometer body has a strong enough pull that nearby pebbles and dust feel it and drift toward it. That makes the big get bigger, a runaway effect. Hundreds, maybe thousands, of these kilometer to hundreds of kilometers bodies, called planetesimals, whirled around the Sun on slightly different paths. Because their orbits weren't perfectly aligned, they crossed each other. Collisions were constant. Some encounters were gentle mergers. Others were catastrophic, shattering bodies into fragments that later reaccumulated. Over a few million to tens of millions of years, this chaos sorted itself into a smaller number of large objects called planetary embryos. Think Moon-sized to Mars-sized bodies. Each embryo had cleared a little lane in the disk and was still absorbing anything smaller that wandered too close. But the inner system wasn't perfectly neat, so these embryos also interacted with each other. Sometimes two would collide in a slow, merging impact. Other times they'd hit at an angle, stripping off mantles or spinning each other up. Our own Earth was not born full-sized. It grew through several of these giant impacts. The most famous one is the Theia impact, a Mars-sized body that likely struck the proto-Earth late in this phase. That collision was so powerful it melted large parts of both objects and threw a ring of material into orbit. That ring, over a short time, clumped together to form our Moon. So the inner solar system's story is not four planets appeared. It's closer to a crowd of rocky bodies fought, merged, and sometimes exploded until only four big ones were left. And because the Sun had already blown away most of the inner gas, none of those rocky worlds could puff themselves up into mini Jupiters. They stayed dense and solid, just the way we know them now. While the inner zone was smashing rocks together, the outer zone was playing by a different rulebook. Out past the snow line, there was more solid material to start with because dust grains were coated in ices. Frozen water, carbon dioxide, methane, ammonia. Those ices made the building blocks bigger, stickier, and more abundant. So the first step, making a solid core, went faster out there. A core could grow to several Earth masses more quickly than an inner planet embryo could. That speed mattered because the disk itself didn't last forever. The young sun's wind and radiation were blowing gas away. After a few million years, the thick gas disk would be gone. Any world that wanted to become a gas giant had to build a big core and start grabbing gas before the supply disappeared. Jupiter seems to have won that race. Its core reached a critical mass early, and its gravity began pulling in the surrounding hydrogen and helium. Once that process starts, it runs away. More mass means more gravity, which attracts more gas, which increases mass again. That's how we got a planet more than 300 times the mass of Earth. Saturn followed a similar path, a little slower and a little less massive. Farther out, where the gas was thinner and the building slower, Uranus and Neptune built big, icy, rocky cores, but didn't manage to grab as much hydrogen and helium before the disk was gone, so they became ice giants instead of true gas giants. But the important thing for the solar system's history is that these massive outer planets didn't just sit quietly in their lanes. Their gravity reached inward and outward. As they grew, they stirred up the orbits of smaller bodies. Icy planetesimals, distant rocky chunks, and either tossed them inward toward the forming terrestrial planets or flung them outward into what would become the Kuiper Belt and Oort cloud. Some models even suggest that Jupiter may have migrated inward a bit and then back out again early on, like a heavyweight walking through a crowded room, rearranging everyone else's path. That stirring is a big reason the inner system went through a heavy impact phase. It also explains why we have belts of leftovers. Where the giant's gravity kept things too agitated, no single planet could form, so the debris just stayed as debris. By the time the main planets had taken shape, 4 rocky ones inside, 4 big ones outside, the solar system was still far from tidy. There were countless leftover planetesimals, rubble from collisions, icy bodies from the outer zone that had been scattered inward by Jupiter and Saturn. For tens to maybe hundreds of millions of years, these leftovers rained down on the inner planets in what we call a heavy bombardment phase. We know this happened because the Moon, which has no plate tectonics and almost no erosion, still wears the craters from that time. Many of its biggest impact basins formed in a relatively narrow slice of time, suggesting a spike in impacts. Earth and Mars were being hit too, possibly even more often, but Earth has erased many of its scars. At first glance, this era looks like the opposite of habitable. Giant rocks slamming into young planets, releasing enough energy to melt crust, boil oceans, and throw atmospheres into space. And yes, some impacts would have sterilized large areas, maybe even the whole surface for a while. But there was a helpful side to all this violence. Many of the bodies being thrown inward from the outer solar system carried water ice and organic molecules, carbon-based compounds that are the raw material for biology. Even some asteroids from the middle zone contained water-locked-in minerals. Each impact that didn't completely annihilate the surface added a little more water, a little more carbon, a little more nitrogen. Over time, that could have helped Earth, and to some extent Mars, build up real oceans and inventories of biologically useful chemicals. And as the big planets kept stirring, but also kept clearing, the number of dangerous crossers dropped. The system slowly calmed. Instead of getting hit by 500-kilometer monsters, the inner planets were hit by 10-kilometer or 1-kilometer leftovers. That's still bad on a human scale, but it's survivable on a planetary scale. So this act in the solar system's history is the rough patch, the newly built worlds getting pelted by the debris their own formation created, and at the same time quietly receiving the water and organics that would make them interesting. Without this messy cleanup phase, Earth might have been drier. With too long of it, Earth might never have stabilized. The balance we got, long enough to deliver, short enough to calm, is one of the reasons we can tell this story now. While the main planets were busy finishing themselves, a whole second layer of building was happening around the biggest worlds. Giant planets don't just grab gas, they also build little disks of their own from the material that falls toward them. Picture Jupiter in that young era. Huge, hot, still gathering, surrounded by a thinner, cooler disk of gas and dust, just like a tiny version of the Sun's original disk. Inside that mini-disk, the same rules apply. Small grains stick, grow into bigger chunks, and then into moonlets. That's why Jupiter's big moons, Io, Europa, Ganymede, and Callisto, line up in neat, near-circular orbits, all going the same way, almost in the same plane. They weren't random captures, they were born there in order, as the giant finished forming. Saturn did the same, giving us Titan and a whole family of icy companions. Some moons didn't form so neatly. Farther out, Neptune seems to have snatched Triton, an object that probably formed in the Kuiper belt and got too close. Triton now orbits the wrong way, a sign it was captured, not born in place. Around Earth, the moon's story was different again. One colossal impact, a disk of hot rock, then a single large moon gathering from it. Rings, too, are part of this layer. A moon that wanders too close to its planet can get ripped apart by tidal forces. The broken pieces spread into rings. Or a ring can be leftover material that never formed a moon because it was inside that too close zone. Saturn's rings may be the brightest example, but Jupiter, Uranus, and Neptune wear faint rings too, scars or leftovers of this busy time. Why does this matter for the history of the whole solar system? Because these moons and rings added stability, tides, and sometimes even extra habitats. Earth's moon helped steady our planet's tilt, making long-term climate more predictable, which is good for life. Jupiter's and Saturn's moons became worlds with internal heating: Europa, Ganymede, Enceladus. Each of them a potential liquid water world tucked away in the cold. So as the main disk finished and the big planets settled, they didn't just become lonely balls. They became centers of smaller systems, each echoing the original pattern, disk to clumps to satellites. It tells us that once nature finds a way to build round things from disks, it just keeps repeating the trick at every scale. By now, the inner zone had 3 especially interesting worlds lined up: Venus, Earth, and Mars. They were all built from the same basic ingredients: silicate rock, iron and nickel, a little water, some gases. They all probably got battered by similar leftover debris. They all sat in what we call the inner habitable corridor, close enough to the sun to get warmth, far enough that ice from comets could melt. And yet their fates could not have been more different, and that contrast is a huge part of solar system history. Take Venus first. It's almost Earth's twin in size, so it could hold a thick atmosphere. But being closer to the sun, it received more energy. If Venus ever had oceans or big pools of water, they were closer to the edge of stability. As the sun slowly brightened and Venus warmed, water evaporated faster. Water vapor is a powerful greenhouse gas, so more water in the air meant more heating, which meant even more water in the air, until Venus tipped into a runaway greenhouse. Ultraviolet light in the upper atmosphere split some of that water, and hydrogen, being light, escaped to space. With no good way to bury carbon dioxide, Venus's atmosphere thickened into the crushing, hellish blanket we see now. Mars was the opposite problem. Early Mars clearly had water. We see river valleys, deltas, sedimentary rocks. But Mars is only about half Earth's diameter and just 1/10 Earth's mass. That means it lost internal heat faster. Its core stopped generating a strong magnetic field. Without a magnetic shield, the young sun's wind could strip away the upper atmosphere. As the air thinned, liquid water on the surface became unstable. It either froze or escaped. Volcanism slowed, so Mars couldn't refill its atmosphere as fast. Mars became a cold, thin-aired desert with frozen water hiding in the ground and at the poles. Between those two extremes sat Earth, in a narrower orbit that kept water liquid but not boiling, big enough to hang on to an atmosphere, active enough inside to recycle carbon through plate tectonics, lucky enough to have a big moon to steady its tilt, and shielded just enough by Jupiter to avoid endless giant impacts. So from one disk, 3 similar starts, and 3 very different endings. That tells us the solar system was able to make multiple almosts. Life on Earth wasn't because the disk could only make one good planet. It was because Earth happened to land in the right slot with the right size and the right long-term cooling. The early solar system is easy to picture as noisy. Collisions, migrations, bombardments. But that phase had to end for life to have a long, unbroken stretch to evolve. That ending happened because of 2 slow processes working together. First, the big planets, especially Jupiter and Saturn, finished carving out stable resonances, the preferred orbital patterns where smaller bodies either stay forever or get kicked out. Second, the leftover debris kept getting used up. Each small collision turned 2 dangerous bodies into one bigger, easier-to-track body. Each close pass with a planet either flung the object away or parked it in a belt. Over tens and hundreds of millions of years, the number of objects on wild crossing orbits plummeted. Instead of an inner system full of crossing trajectories, we got 4 tidy terrestrial planets on nearly circular paths. Instead of a thick soup of icy planetesimals beyond Neptune, we got a structured Kuiper belt with populations locked into rhythm with Neptune. The asteroid belt itself thinned out and split into families. That didn't mean the solar system became perfectly safe. Earth would still get hit by large objects now and then, and the Moon still shows impacts long after formation, but the difference between a world that can keep oceans for billions of years and a world that gets sterilized every 10 million years is this calming. Earth needed that calm to let liquid water stay put, to let continents form and erode, to let early life try huge numbers of chemical combinations. Mars too needed a break to let its lakes last. Even the outer moons needed consistent tidal pools to maintain their hidden oceans. So in the history, there's a pivot, from a system dominated by violent assembly to a system dominated by quiet maintenance. That pivot is what allowed the next chapters: atmosphere evolution, ocean chemistry, complex life on at least one world. You can think of it like this. Gravity built the playground, but then gravity also had to put the toys away so no one kept getting hit in the head. Beyond Neptune, the solar system changes character completely. Sunlight is weak, orbital periods are measured in centuries, and the material is what the inner system once had but burned off. Ices of water, methane, nitrogen, carbon dioxide, mixed with darker, carbon-rich dust. In the very early days, the region beyond the giant planets probably had far more material, but as those giants formed and possibly migrated, they stirred the outer disk. Some objects were kicked inward, some were ejected to interstellar space. Many were pushed just far enough out to form a wide, flat population we now call the Kuiper Belt. Pluto is one of these, big enough to be round, icy, with an atmosphere that comes and goes, but it's only one of many. Others, like Eris, Haumea, and Makemake, show that dwarf planets are common out there. A portion of these bodies got trapped in stable patterns with Neptune, 2-to-1 or 3-to-2 resonances, and will likely stay there as long as the Sun lives. Another portion was flung onto stretched, tilted orbits we group as the scattered disk. Even farther out, probably created by the same early flinging, lies the hypothetical Oort cloud, a spherical swarm of comets tens of thousands of times farther from the Sun than Earth. Those are the solar system's cold archives. Because they're so far and so cold, their chemistry barely changed in 4.5 billion years. When one of them is nudged inward, by Neptune, or a passing star, or even the galactic tide, and we see it as a long-period comet, we're watching the oldest ices of our system vaporize in real time. That outer structure tells us two things about our history. First, planet formation didn't end cleanly at Neptune. The giant's gravity smeared the edge into belts and clouds. Second, the solar system was vigorous enough in its youth to throw material truly far, filling a huge sphere around itself. That means our system has a long memory. Even after the Sun is old and dim, some of those outer bodies will still be orbiting, still carrying the signature of the disk we started with. For almost all of its 4.6 billion year life, the solar system was silent about itself. The planets orbited, the comets drifted, the asteroids bumped and spun, and no one knew. Mars dried out, and still no one knew. Volcanoes on Io erupted into Jupiter's shadow, and no one knew. Ice shells on Europa and Enceladus flexed and cracked over warm, dark oceans, and no one knew. Everything we've just described, collapsing cloud, blazing young sun, planetesimals smashing together, giants bullying the small bodies, the inner zone calming, all of that happened without a single eye to see it. Then, late, very late, on one of the small rocky worlds in the inner, comfortable band, chemistry did something unusual. It built cells, then built multicellular creatures, then built nervous systems, then built brains that could remember, compare, and imagine. That brain, sitting on a planet that happened to keep its oceans, began to look up. First it saw wandering stars, the planets, and tracked them carefully across the sky. Then it guessed models. Maybe we're in the middle. Maybe the Sun is in the middle. Then it made lenses to see farther. Then it made math to describe orbits and gravity. Then, in just the last blink of solar system time, less than a millionth of the system's age, it made machines that could leave the planet and go look. That is part of the history too, because from this point on, the solar system is not just evolving, it is being read. The Moon, once just a bright disk, became a record of the early bombardment when humans walked on it and brought pieces back. Mars, once a red dot, became a dried river world when orbiters mapped its valleys and landers found rounded pebbles and sedimentary layers. Jupiter's moons, once points, became volcanic, icy, ocean-bearing worlds when Voyager and Galileo flew past. Saturn's rings, once just pretty, became systems of colliding ice grains. Even the asteroids turned from little stars into lumpy, ancient building blocks when we actually flew to them. In other words, the last tiny slice of solar system history is the slice where the system started to remember itself, because a species on Earth built tools to recover the early chapters. We sent MEVEN to find out how Mars lost its atmosphere. We sent Dawn to Vesta and Ceres to see what half-made worlds look like. We sent New Horizons to Pluto to see what an icy dwarf can sculpt in the dark. Each of those missions was a way of asking, is the story we're telling about the disk, about the bombardment, about the drying of Mars, about the scattering of the outer belt, actually true? And each time, the rocks said yes. The deltas in Jezero and Gale look like Earth deltas. The craters on the moon line up with a period of heavy impacts. The layered deposits on Mars show that water lasted more than a day. Even the composition of comets matches what we'd expect from ices preserved in the cold. So now, in this late chapter, the solar system is not just a set of moving masses obeying gravity, it is a checked, tested narrative. And quietly, that changes the system's future too. Because once a world makes beings that can launch rockets, the clean, untouched surfaces of other worlds are no longer guaranteed. We have to decide to land gently, to sterilize our machines, to keep some places pristine. We already do this with Mars because we know it once had water and might still have sheltered niches. That's planetary protection, and it's part of the modern solar system story. The system created planets. One of those planets created explorers. The explorers now have to keep from smearing their own biology across the pages they're trying to read. Add to that the fact that we are now tugging at small asteroids with planned deflection tests, sampling from Bennu and Ryugu, talking about mining metal-rich bodies. All of that is the solar system entering a feedback phase. For billions of years, only gravity and sunlight shaped orbits and surfaces. Now technology is a tiny new force. It can't move Jupiter, but it can move a 500-meter asteroid. It can't heat Europa's ocean, but it can melt a hole in the ice to taste it. So when we tell the history of our solar system, we should end not with Mars freezing or the Kuiper Belt drifting, but with this. One small world got stable long enough to grow mines, and those mines started to reorganize their own neighborhood. That's not separate from the story. It's the natural late stage of a system that made a planet with long-term water, gentle sunlight, and enough time for curiosity. When we look at the solar system today, it's easy to think the planets were set once they finished forming, like marbles on a table. But what really happened is that every rocky world got a second, quieter stage of evolution that happened from the inside out, and that stage decided whether a planet could keep an atmosphere, keep water, and keep its surface friendly for a long time. Right after formation, rocky planets were hot, really hot. They'd just been built by violent impacts. Many of those impacts melted big chunks of their crust and mantle. Short-lived radioactive elements like aluminum-26, present in the early solar system, dumped extra heat into them. Heavy metals like iron and nickel sank toward their centers, releasing gravitational energy as they did. All of that meant a young Earth, a young Venus, and a young Mars were not cold balls. They were layered, convecting, slowly cooling spheres. As they cooled, they differentiated, iron to the core, silicates to the mantle, lighter stuff toward the crust. That separation wasn't just sorting, it set up moving metal in the centers of some planets. Moving, rotating, electrically conducting metal is how you make a magnetic field. Earth did this very well. Its outer core stayed liquid, its inner core slowly solidified, and the motion in that metallic layer generated a global magnetic field that stretches far out into space. That field deflects much of the solar wind, so the solar wind doesn't slam straight into our upper atmosphere and strip it away. Mars, being smaller, cooled faster. Its core seems to have lost the vigorous motion needed to keep a strong magnetic field running. We can see evidence on Mars's crust of a field long ago. Some rocks are magnetized, but the global shield is gone now. Without that shield, the sun's charged particles have an easier time blasting away the top of the atmosphere, molecule by molecule, century by century. Over billions of years, that matters. Venus is trickier. It's Earth-sized, so it should have stayed warm inside, but its slow rotation and different internal dynamics seem to have led to a weak or absent global field. The result is two inner planets, Mars and Venus, that did have atmospheres and probably had water, but that couldn't protect those atmospheres as well or recycle them the way Earth could. Add to that the different surface conditions, Mars cold and losing air upward, Venus hot and losing water upward, and you get runaway divergence. So in this act of solar system history, we zoom inside the planets and admit something important. The story isn't just orbits and impacts, it's furnaces, metal oceans, and slow cooling. A planet that stays hot enough inside can keep volcanoes going for billions of years, and volcanoes are an atmosphere's backup plan. They bring out new carbon dioxide, new water vapor, new sulfur. A planet that seizes up too early becomes geologically quiet, and a quiet planet slowly loses the gases it has without replacing them. That's why Earth, with plate tectonics and a churning mantle, can keep adjusting its air, while Mars, with local volcanism but no global engine, became a museum. The solar system gave each planet its starting mass, but their insides decided whether they would stay alive at the surface. Once the planet's interiors settled into their long cool-down, the stage was set for the next slow transformation, turning bare rock into worlds with skies and maybe seas. None of the rocky inner planets kept much of the original hydrogen-helium gas from the Sun's disk. They were too hot and too small, and the Sun's wind was too strong, so they had to build new atmospheres from scratch. The first step was outgassing, volcanoes and ever-cooling crusts releasing water vapor, carbon dioxide, nitrogen, sulfur compounds, and other trace gases trapped inside from formation. Picture early Earth under a sky full of steam and CO2, with lightning and rain and no oxygen to speak of. As Earth cooled, that steam condensed and fell as rain, and it rained enough, over enough time, to fill the low basins and make permanent oceans. At the same time, CO2 dissolved into those oceans and became locked up in minerals. That alone would have made Earth milder than a pure CO2 world. But Earth went further. With plate tectonics, weathering of rocks on continents pulled CO2 from the air, rivers carried the carbon into the ocean, and subduction eventually buried it. Volcanism later returned some of it, making a grand, slow CO2 cycle. A thermostat, as we said before. Venus, without that thermostat and sitting closer to the Sun, heated enough that its early water was pushed into the upper atmosphere, broken apart by sunlight and lost. With no oceans to absorb CO2 and no plate tectonics to bury it, CO2 stayed in the air, making it hotter, driving off more water, and locking the planet into a super greenhouse state. Mars, which probably outgassed its own early atmosphere and even supported rain or snowmelt, bled its air away as its field died and as its gravity failed to hold lighter molecules. Its water either froze into the ground and polar caps or escaped. That's the fork in the road the solar system set up. Same starting recipe: rock, trapped volatiles, heating, cooling. But different balances of sunlight, mass, and internal activity produced a soft blue Earth, a burnt orange Mars, and a glowing yellow Venus. Meanwhile, the outer solar system was running a different atmosphere game. The giants, which had pulled in hydrogen and helium from the start, kept thick envelopes that dwarf anything we have on Earth. Their atmospheres are more like miniature portions of the Sun, with complex cloud decks, storms that last centuries, lightning in hydrogen storms, and high-speed jets. Even their moons, especially Titan, could hold thick air because they were cold enough that molecules moved slowly and couldn't escape. Titan's nitrogen-rich sky is a reminder that atmospheres don't only belong to Earth like planets if you place a world far enough from the Sun. All of this tells us that the solar system's middle age was an age of sculpting air and water, some planets gaining permanent seas, some losing them, some burying carbon, some freezing, some building hydrocarbons in the dark, some never letting liquid water touch their surfaces. When we look across the system now, at Earth's navy blue, Mars' thin pink, Venus's thick beige, Titan's orange haze, we're seeing the long consequences of where the disk was warm, where it was cold, how big a world was, and how long it kept its interior moving. Up to this point, the solar system's history has been told by gravity, heat, and chemistry acting on their own. But on at least one world, and maybe one day we'll find it happened in smaller, hidden ways on Mars long ago, or in an ice-roofed ocean. Life joined in and started editing the script. Early life on Earth was not flashy. It didn't build forests or animals or brains. It was microbial, single-celled, living in the oceans, using the energy it could get from chemicals in water or later from sunlight. But even tiny cells can make huge planetary changes if you give them enough time. Some of Earth's earliest microbes began doing photosynthesis, taking in carbon dioxide and water and using sunlight to make sugars, releasing oxygen as a waste product. At first, that oxygen reacted with iron in the oceans and with volcanic gases, so it didn't build up in the air. But the microbes kept going. Over hundreds of millions of years, oxygen started to accumulate in the atmosphere. That event, the Great Oxygenation Event, was a turning point not just in biology, but in the solar system's story, because it made Earth's air totally different from that of Mars or Venus. Oxygen is reactive. It rusts things, it burns things, it allows high-energy metabolisms. It also makes ozone in the upper atmosphere, which protects the surface from harsh ultraviolet light. That made land a more welcoming place later on. So life, which the solar system had quietly made possible by giving Earth long-term water and a stable orbit, turned around and reshaped Earth's surface chemistry. Later, plants and then whole ecosystems changed how fast CO2 was taken out of the air. Animals, by burrowing and mixing sediments, helped soils form. Even shells from ocean creatures locked carbon in rocks. In other words, once life appeared, Earth's geology, oceans, and atmosphere started moving to a biological rhythm as well as a tectonic and solar one. That never happened to that extent on Mars, because Mars didn't stay wet long enough for life to take over. It never happened on Venus, because Venus became too hot for the chemistry life uses. It didn't happen on Mercury, which is basically a baked, airless core. It didn't happen on the Moon or the asteroids. It's possible a smaller, slower version is happening right now under the ice of Europa or Enceladus, where vents could be feeding microbes, but if it is, it's sealed away and doesn't reach space. That makes Earth the oddball product of the solar system. Not just a planet with water, but a planet whose living layer feeds back on the non-living layers. And this is important for the history. Once life is reshaping a planet, that planet becomes easier to detect from far away. If some distant civilization looked at our sun the way we look at other stars, they might see Earth's oxygen, methane, and water signatures and say, that one is different. Our solar system, by sheer chance of distances and masses, made a world that can advertise its life to the rest of the galaxy. And because life eventually made humans, and humans eventually made telescopes, rockets, sample return missions, and even sleepy science channels, the system created something that can now plan its own next chapter, whether that's deflecting asteroids, seeding other worlds, or just keeping Mars pristine until we're ready. That's the final twist. The solar system began as blind physics, but it produced at least once something that can choose. After the main planets settled into their lanes, and after Earth and Mars finished most of their surface shaping, the solar system didn't just go silent. Out in the cold, beyond the giants, there was still a slow traffic of icy bodies, comets, dwarf planets, and scattered objects that kept dipping inward and then fleeing back to the dark. These bodies were born from the same disk as everything else, but they kept the earliest chemistry locked in ice because they never warmed up. When Neptune and the other giants tugged on them, some of them were tossed into stretched orbits that take hundreds or thousands of years to complete. Every time one of those long-period comets swings inward, we get to see a little time capsule from 4.6 billion years ago start to sublimate, blowing off gas and dust, lighting up a tail. That isn't just pretty. It's proof that the outer reservoir is still feeding the inner system with ancient material. Even today, micrometeorites and tiny dust grains from comets fall on Earth's atmosphere every day, adding a fine rain of extraterrestrial material to our oceans and soils. Some of those grains carry complex organic molecules formed in interstellar space or in the early solar system. So in a very slow, very dilute way, the system is still mixing its ingredients. On top of that, the orbits of the outer planets are not perfectly isolated. Resonances between Jupiter, Saturn, Uranus, and Neptune can, over millions of years, nudge a Kuiper Belt object into a less stable orbit. A passing star, even very far away, can tweak the outermost comets and send a few inward. The galaxy's own gravity can slowly reshape the cloud of distant objects. All of that means the solar system is still exchanging material between its deep cold pantry and its warm inner kitchen. For early Earth, that trickle may have delivered extra water and carbon. For future Earth, it means there will always be a background risk and opportunity of incoming ice and rock. Even Mars and the Moon still get peppered by these messengers, which is why we see young craters on top of old ones. In the history we're telling, this matters because it shows the system never became perfectly walled-off zones. It stayed permeable. The warm inner worlds, the giant planets, and the far-off ices are all parts of one machine that still trades parts, even in middle age. And it tells us something else. If life ever arose independently on Mars, or stayed living in an icy moon's vent, then high-speed impacts and ejecta could, in theory, move tiny fragments of that life to other places, lithopanspermia, but stretched across billions of years. It's not guaranteed, but the mechanism is there. Rocks get launched, drift, and land. Our solar system is, and has always been, a place where material can travel absurd distances given enough time. While the sun warmed the inner 4 rocky planets and the giant planets stirred the belts, some of the most stable, long-lasting environments in the whole system formed where almost no sunlight reaches, underground. We usually picture habitability as something that happens where light hits water, like Earth's surface. But in the solar system's slow evolution, it turned out that tidal heating, radioactive decay, and leftover formation heat could keep water liquid under ice for billions of years, far from the sun. Europa is the poster child, a bright, cracked shell of ice orbiting Jupiter, flexed by its parent's gravity and by the gravitational tug of other moons in resonance. That flexing is constant kneading. It turns mechanical energy into heat. That heat keeps a global ocean liquid beneath tens of kilometers of ice. Enceladus, smaller and even farther out, does something similar around Saturn. We know it because we've seen it spraying salty water into space from its south pole, a vent directly sampling a subsurface sea. Ganymede, Callisto, Titan, Several large moons show signs of hidden oceans, layered between ice shells. These oceans are shielded from radiation, buffered from space weather, and supplied with chemical energy from rock-water interactions at the seafloor. In other words, they're the kind of steady, protected habitats that Mars could only dream of once its surface froze. In the context of solar system history, that's a huge point. As the system aged and got colder overall, as Mars lost surface water and the inner zone became biologically dominated by one world, new potential habitats were quietly rolling along in deep orbit, powered not by the sun but by gravity and chemistry. That means habitability in our system isn't a single spike early on. It's a set of overlapping windows, early Mars. Open, early Earth, open, icy moons, open for an incredibly long time. Even dwarf planets like Ceres may have had, or still have, briny pockets. So the system didn't just make one chance for life and move on, it scattered chances at different depths and temperatures. And because these places are sealed, they might preserve conditions more faithfully than Mars's surface, which has been sandblasted for eons. When future probes melt through or land near vents and taste those oceans, they'll be reading a chapter of solar system evolution we've only been guessing at. The chapter where cold worlds made warm rooms. Once the big dramatic events calmed, the giant impacts, the sweeping migrations, the faces of the planets and moons didn't freeze in time. They kept changing, but in subtler, slower ways that over millions of years add up. On Earth, plate tectonics recycles crust, raises mountains, opens oceans, and erases craters. Wind, rain, ice, and life itself grind rocks to sediment. So even though Earth is as old as Mars, its surface looks younger because it's constantly resurfaced. Mars, with no global plate tectonics and a thinner atmosphere, works differently. Its giant volcanoes, like Olympus Mons, got to reach extraordinary heights because Mars' crust didn't move under them. Its canyons, like Valles Marineris, stayed open. But dust storms, seasonal CO2 frost, and slow creeping of sand dunes keep smoothing and moving material. Over billions of years, that's why some old craters on Mars look softened rather than sharp. Aeolian wind processes gave them rounded shoulders. Even the Moon, which has no air and no water, is being weathered. Micrometeorites constantly pepper it, turning rock into regolith. Temperature swings crack boulders. Electrostatic effects can even make fine dust levitate. On icy moons, tiny grains falling from rings can paint surfaces, and slow freezing and thawing of near-surface ices can change textures. All of these small processes are powered by the sun, by orbital cycles, or by the gradual cooling of interiors. They're the system's maintenance mode. This is important historically because it means the records we read today are a blend of early violent writing and later gentle editing. A delta on Mars might still look like a delta, but sand has blown over part of it. A crater on the Moon might still show the big impact, but its floor has been softened by billions of years of tiny hits. So when we interpret the past, we have to undo both layers, the big events and the slow smoothing. That's why sending rovers and landers matters. Orbiters see the broad strokes, but ground truth tells us how much slow weathering has happened. It also means that, in the far future, if no one intervenes, the inner rocky worlds will keep getting rounder, smoother, dustier, and, in Earth's case, rearranged by tectonics. The solar system didn't stop sculpting once the planets formed, it just switched to fine tools. Compared to Jupiter's gravity or the Sun's heat, our impact on the solar system is small, for now. But it's part of the story because it's the first time any body in the system has chosen to move something. We've already done it. We crashed impactors into the moon to look for water. We slammed DART into the asteroid Dimorphos to test deflection. We've scooped samples off Bennu and Ryugu, changing their surfaces. Every spacecraft we leave on Mars, every rover track, every drill hole is a tiny alteration to a world that was untouched for billions of years. On Earth, our changes are massive. We alter the atmosphere, move sediments, build cities. But those are local to our planet. In space, we're just beginning. In 1,000 or 1,000,000 years, if civilization lasts, we could be nudging more asteroids, mining metal-rich bodies in the belt, building habitats near Lagrange points, even warming parts of Mars. All of those are future tense, but the fact that they are possible at all comes straight from the history we just told. A calm, stable solar system with long-lived orbits gave life enough time to evolve intelligence. That intelligence figured out gravity, built engines, and now can alter the very orbits that once dictated everything. This inversion, from being shaped by the system to shaping the system, is the natural late chapter. It also raises a new kind of planetary protection problem. Not just don't contaminate Mars, but don't knock debris into dangerous orbits. Don't strip mine a body that is scientifically unique, and don't block sunlight where you don't mean to. In other words, we've entered the ethics phase of solar system history. The rocks don't care, but the knowledge does. We now know enough to ruin or preserve clues about the early disk, about Mars's water, about Europa's ocean. So the history becomes partly a story of restraint. The same system that turned dust into worlds turned worlds into mines. Now the mines have to decide how much of the dust to world story to keep intact. Stars like our Sun are steady on human timescales, but on billion-year timescales they evolve. As the Sun fuses hydrogen into helium, the helium ash piles up in the core, making it denser and hotter. That makes fusion go a bit faster, which makes the Sun a bit brighter. It's a gentle creep, but it matters. When the solar system formed, the Sun was dimmer, maybe about 70% as bright as today. Yet Earth had liquid water, which is a puzzle we call the faint young sun paradox. Likely Earth had more greenhouse gases then to keep it warm. As the Sun brightened, Earth's CO2 could drop, through weathering and life, and keep surface temperatures in a good range. That balancing act won't last forever. In maybe 1 billion years, the Sun will be bright enough that even with very low CO2, Earth will start to lose water to space. The habitable zone, the ring around a star where liquid water can exist on a rocky surface, will have moved outward. Mars might find itself in a slightly better spot for a while, but Mars has so little atmosphere that it may not take advantage. The icy moons could see slightly more surface heating, but they're mostly controlled by tides, not sunlight. So the inner solar system's present habitability is a temporary alignment. Sun bright but not too bright, Earth's thermostat still working, life still able to modulate the air. In the far future, the Sun will expand into a red giant and swallow or scorch the inner worlds. Then it will shed its outer layers and become a white dwarf, leaving the surviving planets in wider, colder orbits. That is the last stellar-driven chapter. The central fire that set all the temperature zones in the disk will swell, fade, and change the rules again. Some distant icy bodies may briefly thaw as the red giant phase increases luminosity. Some planets may get destabilized by the Sun's mass loss. Comets in the far cloud may drift away entirely. The neat set of orbits we admire now is not eternal. The same physics that made the system will eventually unmake parts of it. Our whole comfortable epoch, with Mars rovers, Saturn rings, Jupiter storms, and Earth oceans, is a middle, not the end. When most of the volatile, dramatic processes have run their course, when Earth is tectonically quieter, when Mars is completely frozen, when the gas giants have cooled more, the parts of the solar system that will still be telling the clearest story of the beginning will be the belts. The asteroid belt, the Kuiper belt, and whatever remains of the inner Oort cloud. Those places never got hot enough or crowded enough to finish making planets. They also never got active enough to erase their own surfaces. So billions of years from now, even as the inner worlds are transformed by the sun's aging, those belts will still be full of half-made, never melted, lightly processed bodies. Anyone, us, or someone who finds the system later, will be able to pick up a carbonaceous chondrite-like body and read in its minerals the temperature and chemistry of the early disk. They'll be able to see water-altered asteroids and say, water was moving around early. They'll be able to look at families of asteroids that share orbits and compositions and reconstruct ancient collisions. The Kuiper belt especially will stay a catalogue of the outer disk. Icy surfaces processed only by radiation, maybe with thin frosts that come and go. Even if the sun's red giant winds strip some of them, many will remain in long, cold orbits. That's why in our time, we work so hard to visit them now, because they are pure pages. Pluto, Arrokoth, Ceres, Vesta. Each one is a different accent of the same ancient language. Solar system history is lucky in that way. It left its notes scattered and preserved, not all in one fragile place. When astronomers started finding planets around other stars, something surprising happened. Most of them didn't look like our solar system at all. They found hot Jupiters, giant planets snuggled right up next to their stars. They found systems where several super-Earths, planets bigger than Earth but smaller than Neptune, all huddled closer than Mercury is to our Sun. They found stars with just debris disks, stars with one loner planet, stars with wildly tilted orbits. And that told us something very important. The way our solar system turned out is not the default. It's just one of many ways to turn a collapsing disk into worlds. That means the details of our history actually mattered. The fact that Jupiter formed where it did, not way farther in, not way farther out, mattered. The fact that Saturn formed too, and that the two of them probably tugged on each other in a way that stopped Jupiter from migrating all the way inward, mattered. If Jupiter had fallen inward like the hot Jupiters we see around other stars, it might have bulldozed the inner disk, thrown out the building blocks of Earth, or left only one rocky planet in a bad orbit. If the gas in our protoplanetary disk had lasted longer, the giants might have had more time to move around and rearrange everything. If it had disappeared faster, maybe Saturn or Neptune would never have gotten big. Even the asteroid belt, that messy band of leftovers between Mars and Jupiter, is a sign of this delicate balance. Jupiter stirred that region so much that a full planet couldn't grow there, but it didn't stir so violently that it ejected every last rock. It left us a catalogue of primitive, half-baked bodies. Out beyond Neptune, the same is true. The Kuiper belt is full of objects in neat resonances with Neptune because Neptune migrated just enough, in just the right way, to capture them instead of flinging them all away. Put differently, our solar system is the story of a disk that avoided extremes. The inner zone stayed quiet enough for 4 small planets to finish growing. The outer zone made its giants, but not too close to the sun. The gas dispersed soon enough to freeze the layout before the giants could wreck it, but not so soon that nothing big could form. That kind of just enough, not too much setup is exactly what you want if you hope for a long-lived, temperate, water-holding world like Earth. Because of that balanced history, we got billions of years of relative calm in the inner system, a steady sun, and big outer planets that deflected some of the worst incoming debris. So when you hear history of our solar system, don't imagine a single path that had to happen. Imagine a branching tree of possibilities. Giants migrating inward, giants never forming, inner planets getting smashed, and realize that we happen to live in one of the branches that let oceans sit still for eons. That's the branch that let life appear, and let life become aware, and let awareness build telescopes, and let telescopes tell this story. Our system is not perfect. We still get hit by asteroids, Mars froze, Venus cooked, but it is unusually generous to complex life compared to many of the compact, chaotic systems we see elsewhere. That's why this act belongs in the story. It reminds us that the solar system we fall asleep to each night is not just what disks do. It's what this disk did under these timings, with this star, in this part of the galaxy. We got room to breathe because the giants didn't crash the party. It would be nice if, once the planets formed and the bombardment quieted down, we could say, there, the solar system is finished. But space is never really finished, it just gets slower. Every planet and moon is still losing heat from its birth. Every orbit is still being tugged by every other body, even if only a tiny bit. Tidal forces are still trying to round things out, lock rotations, and pull moons into safer or less safe paths. Take Saturn's rings, bright, crisp, and iconic. We know they can't be as old as the whole solar system in their present form, because collisions and sunlight and Saturn's own gravity should darken and disperse them over time. That means they were either replenished or formed later, maybe from a moon that got too close and was torn apart. In the future, parts of those rings will drift inward and rain onto Saturn, while other parts may clump and make tiny moons again. Mars, which looks so frozen and still, is quietly pulling Phobos, its inner moon, closer. Phobos orbits faster than Mars rotates, so Mars's gravity is stealing its orbital energy. In tens of millions of years, Phobos will get so close that Mars will tear it apart, and for a while, Mars will have a ring too. A brief, beautiful echo of its own disk past. Earth, meanwhile, will keep shifting its continents as long as its mantle can convect. That means mountain ranges that exist now will erode away. Oceans will open and close, and the record of our time will be shuffled down into the crust. Even the moon, airless and quiet, is feeling tiny quakes as it continues to cool and shrink. On icy moons, the slow decay of radioactive elements keeps water from freezing solid. On Enceladus, that, together with tides, powers the geysers that spray into Saturn's E-ring. And no matter how calm things get, the solar system keeps throwing stones. Asteroids in the main belt feel sunlight unevenly, which over long timescales can change their spin or nudge their orbits. The Yarkovsky effect. And that can eventually send them toward resonances that fling them inward. Comets still fall from the distant dark. Even the galaxy itself, as our system moves through it, can disturb the most distant comets and send some sunward. All of that is to say, finished in space is a human word, not a cosmic one. The system is coasting, not frozen. And in that coasting, slow but steady, the features we use to read the past will keep getting blurred, buried, rearranged. That's why scientists rush to map Mars's deltas, to core the polar ice, to look under Europa's crust. Because even though those things have lasted billions of years, they won't last forever. Cooling, shrinking, tidal flexing, ring spreading, moon spiraling. These are the last geologic whispers of a system that used to shout. They're gentle, but they keep the story moving forward, even if the big drama has ended. For most of solar system time, the only archives were rocks, ices, and orbits. A crater told you there was an impact. A clay layer on Mars told you there was water. A family of asteroids told you something big got smashed. But now, right at the very end of this long chain of events, the system has grown something that can copy its own records. That's us, or more precisely, our instruments. When Apollo astronauts scooped regolith from the moon and brought it home, they gave us a precise date for giant impacts there and proved that the moon and Earth are made of very similar stuff, supporting the giant impact idea. When we found Martian meteorites on Earth and read their trapped gases, we got samples of Mars's crust and atmosphere without even going there. When OSIRIS-REx brought back material from Bennu and Hayabusa 2 from Ryugu, we suddenly had actual pieces of the primitive building blocks, the kind that never became planets, sitting in Earth labs. Perseverance, right now, is drilling cores from an ancient river delta in Jezero Crater, the same kind of place on Earth where microbial life loves to get buried and preserved, and caching them for a future mission. That's a human being saying, these layers are exactly the ones 4 billion-year-old Mars life would have used, so let's save them carefully. And because data is easy to copy, once we've mapped a canyon on Mars, or a crack on Europa, or a dune field on Titan, that snapshot can live in 1,000 places even if the original erodes, or we later drive a rover over it, or we build a human habitat nearby. We are, in a sense, taking out insurance on the solar system's memory. We're also linking fragments together. A single sedimentary rock on Mars makes more sense if you also know the orbiter's mineral maps, the meteorite's chemistry, the sun's early wind strength from MAVEN, and the impact record from the moon. None of those single pieces could by themselves tell you the whole story. Together, they do. That's why space agencies obsess over sample context and clean handling. Because we're no longer just looking, we're preserving the best pages of a 4.6 billion-year-old book so they can be reread, redated, and reinterpreted by people who haven't even been born yet. This is a brand new phase of solar system history, self-archiving. The system made planets. One planet made minds. Minds made machines. Machines now make durable, shareable memories of the planets. Even if the sun in 5 billion years swallows the inner worlds, even if future engineering remakes Mars, even if parts of the asteroid belt get mined, there will be a chain of knowledge. Rock samples in deep storage, maps, spectra, high-res images that show what the system looked like during its quiet, habitable middle. And because we can transmit and store that knowledge off-world, the solar system's own story no longer depends on the continued survival of Earth's surface. That's a huge leap. A system that used to forget, craters eroded, atmospheres blown away, seas frozen, can now remember with help. It is the first time the solar system has a backup. So here we are, at the end of a very long timeline, and it's worth telling it once more, not fast, not flashy, just smooth, so it sits in your mind while you drift off. Once there was only a quiet patch of gas and dust in our galaxy, cold, dark, full of raw elements made in older dead stars. That patch collapsed under its own weight and spun itself flat, and in the middle a star lit. That star blew away the extra gas near it, so only rocks and metals could stay close, while ices and thick gases could gather farther out. In the warm circle, dust hit dust until clumps became boulders, boulders became mountains, mountains became worlds, and some of those worlds hit each other so hard they made moons. In the cold circle, cores grew fat on ice and then wrapped themselves in the gas that was still there, becoming giants. The giants stomped around for a while, throwing water-rich and carbon-rich bodies inward and flicking leftovers outward to the dark. For a time it was dangerous. Rocks rained down, craters bloomed, oceans boiled and recondensed. But eventually the traffic slowed and the orbit smoothed. 3 rocky planets sat in a row where water could be liquid. 1, too close, baked. 1, too small, froze. 1, in the middle, active inside, shielded above, stayed blue. On that blue world, the chemistry that had been delivered by comets, baked in volcanoes, and stirred in warm seas finally organized itself into cells. Those cells altered the air. The air protected the seas. The seas nurtured more life. Life learned to think. Thinking life looked up and realized it was sitting in the middle of an old, patient machine made of gravity and heat. Then it got curious and started checking. Are there really river deltas on Mars? Did the moon really form from Earth? Did Jupiter really throw stuff around? And every time we checked, the rocks said yes. Now we sit in that tiny blink of an eye moment where the system can describe itself, where a person can lie in bed and listen to 4.5 billion years of events, in order, like chapters. The future will keep happening. The sun will brighten, Mars will get a ring, Saturn's rings will thin, comets will keep falling, and someday the sun will grow old and undo the neat inner layout. But none of that can erase the fact that a single dusty cloud, by obeying simple rules, made a star. 8 major planets, moons with oceans, belts of relics, and at least one species that wanted to remember it all. That's the miracle, and it's a quiet one. The universe likes to turn chaos into structure, and sometimes structure into awareness. Thank you for listening to the whole thing, from the first cold swirl to the last warm thought. Let the planets keep orbiting without you for a while. Sleep well, and good night.